So hello again. I will give this first seminar showing you some of the work that we've been conducting with Charlotte, who's a former PhD student of Tanguy and I, and with colleagues in Neuchâtel for the modeling part, and also geochemists from IPGP in Paris. So, following on what we've seen this morning, we've seen that water is flowing, and René told us everything about it. And when you look into a catchment, you can see that there are some places where water is actually flowing down in the ground, and you can actually see all other places where water is moving up, which is, for instance, the case that you would see on this picture. And the fact that, of course, you have these vertical movements of water is highly related to the position where you are on your catchment, which is what you see basically here, which is if you are at the top of the hill, flows will be mostly downwards, while they would be upwards on the outlet part of your catchment. Well, this is actually the way the water table is located on a catchment is actually important for many reasons, and one of them is, for instance, for vegetation, which is something that you will hear about later in the week. All right, but also, if we want to understand a bit more those flows and really looking at moving from this morning to theory to the really catchment scale, the question is, how do the water organize and what are the flow paths in the groundwater? So, as René said rapidly at the end of his talk, actually what we see most of the time is this type of patterns of the groundwater where you have this representation that has been made long time ago by Toth, as René said this morning, and where what he has shown is that actually because of little changes in the topography, you have different scales of flows that are occurring in the ground. So you would see some small loops with local flows, some intermediate flows, and some very deep and long flows that are more at a regional scale. Well, the fact that water and flows organize that way in the subsurface is important because of, for instance, if you look at surface water, groundwater interactions, you'll see that whether you're situated in the upstream part of a catchment, you would have a connection of the river to the groundwater that might be sometimes, and that sometimes might not be, yielding intermittent streams, while the most you go downstream of a catchment, the most you are going to have rivers that are actually fed by the groundwaters due to all these different flow paths. Well, I like to add this picture, which is a nice study that has been made by colleagues in Paris that's actually showing transport. So what Thomas showed us this morning, which here is a little bit more visual, and it's the idea of the fact that when you have flow, if you add, so the idea is very simple, they add a tracer in this experiment, and you can really see how the tracer is transported in the ground. And the reason why I like this experiment is because it actually shows quite a number of interesting features of groundwater flows. So if you look at all of this, you can see, of course, that you have some particles showed here, of course, with these blue images, that some of them are going to reach very rapidly the outlet part of the catchment, while some of them are going to stay for a very long time in the media. And so this is what is usually conceptualized with the idea of groundwater age distribution, which is that you have young ages here, but here you would have old ages of the water. And it's important to know this distribution because, of course, if you have different times of interactions between the water and the media, for instance, the rocks, then these different water-rock interaction times will have a huge impact on the reactivity, which is something that Jenny will tell us about later in this summer school as well. Of course, it will also have an impact of temperature because deep flows and shallow flows do not have the same temperature, which again is something that Maria will tell us about. But also something that I like is the fact that you see here that if you target on the outlet part of the catchment, you see that there's a mixing of different flow paths, which is this idea that has been several times said, which is that streams are mirrors of the underground processes, because what you can see here is actually, if you monitor this part here, you would monitor actually all of the flow paths that are going to this point. And one important point is that you can see the deep flow path. Most of the time, they actually account for a very small amount of the water in the river. However, if you think of chemistry, then it can have a very important contribution to the chemical loads, for the reason that, of course, as we said, here there is much more time for water-rock interactions and then for higher concentrations in the water. So here you see that actually there is some connections between the way the groundwater flows are designed in the ground and the way they will organize and the reactivity of the catchments. So that's the correlation between the flow, transport, and potentially reactivity. So, yes?
In this picture, you assume homogeneous domains.
Yes,
so it's only the distribution is only due to streamlines.
Yes.
But of course, in aquifers, you have other preferential flow pathways.
Yes, absolutely.
So how do you reconcile this when you decode the ages, for example?
Yes. So it's true that here everything is homogeneous, which is one limitation of this kind of study, which comes to, well, how good is it to try to have a look at this medium as an effective medium where everything is homogeneous. And I would say that it depends what we look at. And for instance, if we think of preferential flow paths, we see and we can see that sometimes we have very deep within the aquifers, we could find something that is not, for instance, ages that is not increasing with depth, but because of preferential flow paths, at some places we could have ages that are much younger. So this is something that, of course, is not represented here, but that's something that occurs in the real world, I would say. Okay, so the question here today that we will work on is, so okay, if the fact that the groundwater flow patterns are actually related to changes in topography, and the fact that these groundwater patterns change the reactivity of the subsurface. So the question today is, what is this interplay between the landscapes on the surface, the underground flow path, and the biogeochemical reactions that are occurring in the groundwater? So to look at these questions, we actually went to one site, that's the Kyoc site, which is located in Guadeloupe, which is an island which is here in the Caribbean Sea. So this catchment here is part of a network, which is the French network of critical zone observatories. So you know that there are some sites that are highly instrumented and that are dedicated to the study of critical zone. So there are networks in America and in France and in Europe, and the one in France is actually called Oscar, and this site is one of them. So this site is actually dedicated to the chemical and physical erosion in tropical volcanic islands, because Guadeloupe is a volcanic island. And the reason why we wanted to ask that question on that website, on that site, study site, is because there is somehow a paradox when we go to Guadeloupe, which is the fact that these tropical islands are the places where the weathering rates are the highest. And yet, the weathered layers are very deep, which means that there is weathering occurring, but let's say everything is already weathered, which of course asks the question, where is the weathering occurring? And also one of the reasons why there is so much weathering is because there is a high rainfall rates, as you can see here, with more than 3 meters per year of rainfall. One important feature also of this study site is the fact that there is here a clear knickpoint, which means that there is a change in topography. And as we said earlier, here we want to investigate the role of the topography on the groundwater flows. And it's thus a very relevant site to go and have a look at the impact of the knickpoint. Yes?
Sorry, can you clarify what weathering means?
Weathering?
Yeah. Is it just erosion or what do you mean by?
Well, weathering is the reaction of water with minerals of the rocks that are going to change these minerals, and that as a result, you have some of the elements of your minerals that are then dissolved ions and secondary phase minerals that are created, precipitating. So it's this reaction that actually, let's say if you want to make it simple, that will transform rocks into soils at the end of the weathering process. Okay, so what did we do on that catchment? So we wanted to see if there are some chemical changes first along the river, and if those chemical changes, as we say that rivers are mirrors of the subsurface, try to test that hypothesis. So what we did, of course, then is to do some river chemical profiles. So we have sampled the river all along the stream, and we measured flow rates, major and trace elements, and the thing that I will talk most about today is the isotopic composition of strontium. So the reason why we went to measure strontium isotopic composition is explained here. So there's been a lot of studies that have been made on the catchments, and they actually show that the isotopic composition of rainfall, which is here, is conserved throughout the weathered layer because it's already highly weathered, while you can see that the isotopic composition of the rocks, which is here basalts, is different. For those that are not familiar with this data, this difference here is highly significant. So it's a very high difference in the isotopic ratio, which means that we have actually a way, a proxy, to see if the water, depending on its isotopic composition, whether it's a water that has only a rainfall composition, meaning that it has never seen the bedrock as it's, or it has an isotopic composition that is the one of the basalt, meaning that it has seen and interacted with the basalt. So that is the first thing that we did. The second thing that we did was to do some geophysical profiles. The idea of that is to get an architecture of the subsurface. I won't tell more about this because you will know all about that in the talk of Thomas in the week. And then the last part, of course, was to do some numerical modeling and see if we could indeed relate the patterns of the groundwater flows to the chemistry and potentially to the topography of the site. One point first, before I get back to my study site, I just want to tell you a little bit more about the model that we have used. Because actually the model that we have used is something new that we are currently developing in Rennes and also in Neuchâtel, where I told you that we've been working with colleagues there. So the idea of, it's like a code that we are creating that is called HydroModPy. And the idea of it is to try to give a tool that is an easy way for critical zone scientists to have an idea about groundwater flows. Because something I did not mention is the fact that most of the people that are looking at critical zone in terms of weathering and these reactions, they do huge simplifications over the way the groundwater flow patterns are designed in the ground. So here what we do is that we do huge assumptions about the chemistry and the geochemistry of the reactions, but we try to represent groundwater flows as best as we can. So that's what we do, and that's what we do using this model that has been developed by the team, as I told you. It's actually pretty easy. You just give your outlets, and it extracts the size of your catchment. It extracts every information about river networks, about topography, about geology, about any data that are available, hydraulic heads, gauge stations, river discharge, everything. Then you set the recharge that you're interested in, you set the hydraulic conductivity, and then you can start running your models. And you have a set of easy maps, yes, that are done.
You say that it downloads the data that is available?
Yes.
Where does it download?
It goes, well, so far it's worked very well in France. We don't know about all the data in the entire world, but it goes on all the public data sets, database, at least in France, to go and directly collect on the net the information that you could get on your catchment. Yes?
You have this kind of thing in our GIS as well, right?
Yes, yes.
But can you do this kind of simulation directly in GIS, or no?
I don't think you can. I mean,
really
the way, the result that you get from here, you can then use them in GIS.
Okay.
And I would say it's better to do it this way than the other way around.
But things like
It's-
topography and whatnot, you can, I think the data is usually
Yeah,
available.
yeah, absolutely. Yeah, that's where you will just get them.
And what you guys have all conductivity map?
No, here you assume and you calibrate hydraulic conductivity, just that you would do for any hydrogeological model. And actually it's so, and then at the end you get, the idea is also to help you have nice maps. So you have, of course, the water table elevation, but also something that, as I said before, we are very interested in is to have an idea of the pass lines, because we said that we think that it's very important to well represent the pass line in the catchments. And also something that we are very interested in, as I said before, is residence time, which is groundwater age, which is something that we actually also measure. So for us, it's very interesting to see if we are able to model and to have age data that actually fits, which is a huge challenge. Yes?
Related to that, I see you're mapping residence time
Yes.
in the stream channels at upwelling zones, presumably.
Yes.
Can you tell me a little bit about how these flow paths with very different residence times are integrated to give a single number in
Yes.
an upwelling zone?
Yes. So maybe I can go just, well, you'll see just right here, maybe how we do it. Tell me if it's not enough to explain but what I wanted to say is another thing that's a bit specific about this model is that we actually want to calibrate the model over river networks, because the idea is that most of the time we don't have hydraulic head data, while most of the time we do have the river network. So the idea was to say, can we, from the river network, have an idea on the hydraulic conductivity? So here is an example with where you can see two catchments that have actually river networks. One here is very well developed, the other one is much shorter, and that this one is very much changing throughout the year, because you can see that everything that's orange is intermittent river, while this one is more or less perennial. And so what we do when we calibrate, so we run the model, and as you can see here, I must go that way, yes. Here we will try to calibrate the model in order to reproduce this. So what you see here is actually, so on the river here we have a draining condition, and then we accumulate flows, which is the reason why we are actually able to measure, to have the flow and also to have the average age, to answer your question of how do we get the age of the water that's going out of the river. So either we just do we can either map single flow paths and their age, or we can try to average them to have the evolution of the age along the stream. Yes?
Just a quick one. What kind of resolution are you typically thinking of here? Like kilometers?
No, much smaller. Well, of course it depends what you want to do, but you can go down to the resolution of your DEM, which would be
100 meters?
30 meters?
30 meters?
Yes, most of the time. But then you can, there are also cases where you can have a much finer resolution, but on a much smaller case. But yeah, so it's your DEM that defines the resolution of your model. So here what you see, just to wrap up on this model, is that, well, the fact that the river network here is much more developed than here is due to the fact that the hydraulic conductivity is lower, but the fact that this one is reacting much more than the other one is because the porosity is very small. So any change, any input of water creates a huge change in the water heads just because the porosity is very small. So this is just to give you an idea of how this model works. And now I'm coming back to our study site. All right, so here are first the data that we have on the chemistry of the river. And what you see here is that it's a very simple mixing diagram, and that you can see that the points of the river actually fit in between these two end members that I've described previously, which is the rainfall end member and the silicate, the basalt end member that I've said before. So it means that indeed the river is a mixing of water that has a composition of the rainfall and of water that has a composition of something that has seen the basalts. And now if we look at the profiles along the river, so here you have the profiles from the outlet so here is the upstream part of the river, and the water is flowing down. as you can see actually here with the topography profile. Here is the knickpoint zone that you see. And so what we see here is that there is in this area, which is the knickpoint, we can see that just after the knickpoint there is an increase in flow rates, which is and at the same time we can also see that just after the knickpoint there is a clear shift in the isotopic concentration and in the isotopic composition that's shifting down. So here we see, well, at least it seems to show that everything that's below the knickpoint is something that's related to some interactions with the basalt, while everything that's upstream of the knickpoint isn't. All right. Then I told you about the fact that we did some geophysics. Just here I will make it simple, because it's already published, but the idea is just that there's been some profiles that have been made, and based on the inversion of seismic travel times, the velocity has been deduced, and from that, to make it simple, when it's like this, when it's the speed here, so here it corresponds to a material that's hard, while here it corresponds to a weathered material. So the idea based on that, we've been able to have an idea of the weathered layer and of the unweathered bedrock layer, and we interpolated it over the whole catchment, so which is what you can see here. And of course, the idea, as I said before, is that every water that's flowing only in this layer, in the first layer, will have a strontium isotopic composition that is the one of the rainfall. Everything that's flowing below would have an isotopic composition that is the one of the basalt. Okay, so now we wanted to put all of this into our model. As you can see, we have here the catchments. This catchment has been divided into these two layers with different hydraulic conductivities, because that is one part of heterogeneity that at least we know exists, so we can't ignore it, which is the fact, okay, we do have two different geological layers, so we must at least try to see if there are changes and differences in the hydraulic conductivities of those two layers. So what we did is that we first considered the homogeneous catchment. We calibrated the hydraulic conductivity on that. And then, assuming a conservative transmissivity, we did some sensitivity analyzing, changing the conductivity of the two layers, which is what you see here, which basically means that we considered our two layers. We considered the first layer in some cases where the hydraulic conductivity is lower, and some other cases where the hydraulic conductivity of the upper layer is smaller and higher. And once again, everything that's flowing in this part has a strontium composition of the rainfall end member and the other one of the basalt end member. So I'll go to the results. So here I'm showing you 3 cases where this one is, well, I should have written it. This one is the K1 over K2 that's below 1, so 0.1. This one is, of course, 1, and this one is 100. For each of the scenario, we want to see how well we can simulate the river and how well we can simulate the strontium composition in the river. And here are the results. So you can see that in this case, of course, we have much more resurgence, much more groundwater outflow, so much more inundated parts in the catchment. And then the most we go here, the most we have a river that's actually only in one main channel. And you can see that, well, we see that it's actually very hard, at least so far, to be able to simulate this part of the catchment, this part of the rivers, but we've been there, and we also actually know that here is very intermittent flows. So with this approach here, that's steady state, I didn't say it, it's not surprising that we are not able to simulate flows in this upper part of the catchment. And now when it comes to when we go to the strontium composition, we can see that in this case, we see that the shift in the strontium composition comes way too early, way in the upstream part of the catchment, and when the most we go towards this type of model, the most we see that we are actually able to simulate the shift of the isotopic composition that is only in the downstream part of the catchment. So here are only 3 cases, but when we did it for several cases, everything is summarized here, and we defined different ways to analyze our results with here a difference that is made on the difference between the observed and simulated stream. Here we see the difference in between the observed and simulated discharge, flow rate. Here it's about the strontium composition, concentration, and here is the difference in the isotopic composition of strontium. And what's interestingly, what we see is that, well, if we only looked at the river, we can see that the river network and actually the river flow rates, well, it tells us that the upper layer has to be more permeable than the lower layer. But it doesn't tell us how much, right? Because all of the results here are more or less, give more or less the same fit. Whether you're here or here, the fit is more or less the same. But as soon as we add strontium compositions, we see here that there is a clear minimum for a certain ratio of K1 over K2. Yes?
A quick question. So for the hydraulic conductivities, have you assumed that they were isotropic, or did you assume
yes,
okay.
yes. But yes, we also tried different scenarios, but here, yes, that's what it is. Okay, so we see actually that, well, here it seems that indeed streams, if streams are mirrors of the subsurface, we can indeed use the chemistry of the river to constrain the hydraulic conductivity of a catchment. All right, and then now, okay, we say that we are able to well calibrate a steady state. Okay, that's interesting enough. But also, now what do we learn? So to see and to try to better understand what we learn, here is the result for our best model, which is the one that I've shown you before, where we have a good match on the isotopic composition of the river. Here are the results that we can only get with the model. So the first thing you can see here is actually the flow rates change along the stream. And you can see here that we actually simulate an increase of the flow rate here and then a huge increase of the flow rate just downstream the knickpoint, which is what we observed before. Another thing here is that we have differentiate in between the flow lines that stay in the upper layer and the flow, which are here in blue, and the flow lines that have entered the bottom layer, which are here in red. What we see here is that indeed in the upper part of the catchment, there is only blue bars, meaning that all the water in the river is some water that has flowed only in the upper layer of the catchment. And here comes the red bars. And the size of the bar is actually related to the residence time, which means that every water that's here in the upstream reach is actually some young groundwater, and the stream in the upper part of the catchment receives only young groundwater, which, as you see here, is about 1 year. However, when you get down to the catchment, to the downstream part of the catchment, you can see here that there is some groundwater getting out of the ground and actually getting into the river that's much older, and with here groundwater age up to 100 years that would actually reach the streams. So that's what we can only get with simulations. And indeed, if we do some measurements, it would be hard. We tried. It would be hard to, we see here we have some tracer telling us, well, there is some old groundwater, but how old is it is, because all of this is a mixing, it's actually a little bit hard to say. Another interesting thing here is that we decide to trace all this old groundwater that's arriving in the stream downstream the knickpoint. Where does it come from? And interestingly, we see that because of the knickpoint, there is some convergence of flows, of deep flow paths that are all of them occurring from the upper part of the catchment, from the edge of the catchment. And if we think about what it means in terms of weathering, it means that every other water that's flowing on the catchments everywhere else stays in the upper layer, meaning it never really weather any rock because it stays in the weathered layer. And the only part of the catchment where there is actually weathering occurring right now is in this upper part of the catchment. Well, what does it say? It actually says that because there is a knickpoint, it seems that this knickpoint there is a topographic control on the flows, meaning that we can see that there are some long and deep flow paths that are converging downstream of the knickpoint, but also on weathering, which means that weathering is actually restricted to this flow path here and weathering only to the stream. And this is interesting because it means that if you get the weathering rates and you calculate it back to the effective area of where it's actually weathering over the catchment, you would get very high weathering rates. And this is interesting because there is always this paradox in between. When you do experiments, most of the time you get very high reaction rates, and when you're on the catchment, then you get very much lower reaction rates. And here it could be one of the reasons why, because actually the surface on which you do have weathering occurring over this catchment is much smaller than you would expect if you would take the entire catchment as a place where weathering occurs. Okay, to wrap it up a little bit, so we've seen that, well, when we were wondering about this interplay, how landscapes, underground flow patterns and biogeochemical reactions all are mixed up and play one with the other, we see that we've chosen an approach where we have oversimplified the geochemistry to try to get a good representation of groundwater flows, which, as I said, is the opposite of what is usually done. And here we see that it's actually interesting because we see that weathering is actually very localized because of the way the groundwater flows or the pattern of the groundwater flow in the subsurface, which itself is due to the catchment morphology. And just to leave it to some open question, which is, well, then how much is geomorphology a driver of the subsurface reactivity and of the quality of the water in the streams? And just to play a little bit, what I did is that we extracted all the knickpoints that are similar in Guadeloupe to the one that we've observed on our study site and say, well, okay, now if we apply the same mixing as we've seen on our study site to all these knickpoints, how much does that influence the water quality of Guadeloupe? And what you see here is that every parts here that are actually colored, not in deep blue, but like in yellow and light blue, is all of these rivers here would actually have a concentration that has been changed because of the presence of the knickpoints on Guadeloupe. So it would show that actually, at least in Guadeloupe, the fact that there are those knickpoints would have a huge impact on the water quality. Thank you very much. Yes, Audrey.
Thank you for your really interesting talk. One little question, just maybe I missed it, but is that resonance time or age at the stream that's upwelling, is it from a groundwater age model or more like resonance times along effective flow paths that are then fluctuated?
Yes, it's we just used particle tracking of the advective flows.
And it's fluctuated.
Yes, that's how. Yeah.
The more deeper question that was fascinating to me at the end is, so if you're saying that this layered system is mainly because of the expression of weathering from the past, over geologic time scales, have you thought about how that evolves with time? Because it seems from your geophysics that it suggests the weathered layer is sort of similar throughout the catchment, but your groundwater flow models for today are suggesting that more weathering might be happening in the bedrock in some places in the catchment due to topography than others. How do you reconcile those two things over geologic timescales?
Yes, I agree, absolutely fascinating, and that's something that we really want to work on now, and which would be, well, now if we take it indeed to deep times, because here what we see is that there would be some co-evolution of the fact that if you have some topography, then that topography would induce some weathering, and then of course we know that the most weathering you have, the most erosion you have, and then you would back change your topography, and then you kind of see that there are some feedbacks going on here, but then how much is it, and over which time scale is it working, and all of this we don't know yet, but it's clearly something that we want to look at in the future. But yeah, these feedbacks is, I agree, I think it's really interesting. Yes?
So in your system, the weather zone is quite deep, right?
Yes.
And this strontium isotopic ratio only changes when it hits the bedrock.
Yes.
So any biogeochemical reaction that actively happens in the weather zone,
Yes.
I think will be highly impacted by the local hydraulic conductivity heterogeneity.
Yes.
But here you assumed constant conductivity in the weather zone.
Yes.
It worked because you looked into strontium.
Exactly. Yes.
So can you comment a little bit about like how important is the heterogeneity of this near surface in biogeochemical?
Yes, in general, you mean?
In general.
Yes. Well, clearly, we took the easiest proxy. That's the advantage with strontium, is that the reaction time to get an isotopic composition of a basalt is very rapid. So it means that indeed, it's almost like at the time scales that we are interested in, it's almost instantaneous. That's why we can say everything that's in the weathered layer has a rainfall composition, and then almost as soon as it reaches the basalt, it gets to the strontium. So our hypothesis works for strontium, but as you say, for other elements, then there would have been like complex different types of reactions occurring that would change those concentrations in ways that we are not accounting for here. So, and it's true that heterogeneity on top of it is something that would change, and I don't know how much the weather, because we have very few cores and clearly not as deep as the bedrock. So it's not very clear how heterogeneous is the weathered layer. I'm not sure it's the most heterogeneous, to be honest. I think that there are places where it's much, much worse, because the rock initially is basalt, and because it's a volcano and it's basalts everywhere. So you could assume that weathering is more or less the same. But yeah, I think it's clearly that's where this type of approach stops, and then that's where, if you want to go a bit further, then of course you would need to add more complexity in the reactive pathways, which here is clearly simplified. Yes.
So this is really cool, and it's making me think about some of the older work about what we understand about flow paths evolving in basaltic landscapes, like Anne Jefferson's work and Camille Bouchez's work. And I'm wondering how this kind of fits into that paradigm of going from a young landscape that has predominantly vertical flow paths to an older landscape that has primarily like lower permeability and more shallow flow paths, and whether that's similar to what you're seeing here or whether you think there's more to the story?
I don't know. I don't know. I mean, I think it's part of the story of how indeed you would change with time, and the conductivities and then the flows, but I don't think it's the whole story, but I think it's somehow added up. But I don't know exactly how to reconcile all these different stories so far.
One thing that, I don't know, just like thinking in real time might be interesting is, I assume that there are deposits, like volcanic deposits at different ages.
Yes, absolutely.
I wonder if the calibrated hydraulic conductivity and the calibrated, like maybe effective thickness that you would get if you calibrated to stream networks in different places.
Yes, absolutely. That's absolutely true, and that's something also very interesting, which is that if there is a gradient of age of the basalts over Guadeloupe, and then which results in the fact that you have an increasing weathered layer and a gradient of the thickness of the weathered layer. And indeed, what we need to do now is to go and get different catchments with similar conditions, except the fact that the weathered layer is increasing, and test the model and see if it still fits. Because as you say, it's indeed, I think, a very important, and it's great that there is this gradient, because it opens really like new opportunity to try to test this kind of ideas on this. Yes, absolutely, you're right. Yeah.
This might be very simple, and I might have missed that. A lot of this was based on the idea that you have two hydraulic conductivity layers. Is there a physical basis to support why there might be two, or is it just it works?
Well, Yes, so the reason why you would expect to have different hydraulic conductivities is just because the nature of the rock is different. And you know, as we've seen this morning, most of the time we actually infer hydraulic conductivity based on the lithology that you're working on. If you're working on a granite, if you're working on sedimentary rocks, you would guess that the hydraulic conductivity is different because the rock has different properties. So I would say that's the underlying assumption, which is that, but what we are doing here is that we actually put a front that's very sharp, right? We say we go from something that's completely weathered to something that's completely unweathered, which of course is not the case. So you could think of something that's actually changing through depth. And we tried that with, for instance, the exponential model of hydraulic conductivity, which is something that's often assumed. But actually the results are very similar to the fact that you assume that the upper layer is more permeable than the lower layer. So it's interesting to see that the way you would design actually your change of hydraulic conductivity with depth is not, I mean, that's not the main constraint. I mean, whether you take this exponential model or 2 layers more or less give the same results. And, but something that's interesting is, do we expect the upper layer to have a higher conductivity or a lower conductivity? And this has been the debate for a long time because basalts, the thing is that you will need fractures to get some flow, but the weathered zone, most of it, like if it's clays, most of the time clays is also considered as something with a very low hydraulic conductivity. So it was not clear, and actually we didn't know whether the upper layer should have a higher hydraulic conductivity or a lower hydraulic conductivity, because there is some debate about that. Some people say it should be one way or the other. So that's why we think that, yeah, at least here we somehow have a clear idea on the fact that it has to be higher on the upper layer, otherwise there's no way we can simulate our strontium concentrations.